Okay, let's start out with this problem. Of course, there's only two angles we need to know. We have the 117 degrees, 37 minutes. That's going to be in a couple other places. Which other two angles are going to equal that? B and C are both going to be 117, 37. A and D are going to be the same. We just need to figure out what that is. How do we do that? Perfect. So we make it 180 degrees, 0 minutes. We subtract our 117.37 from that, which is going to give us 62 degrees, 23 minutes for each of those, A and D. Not so bad. How many of you got that? Cool. Another one for you to try quick. We have a 3/8 inch groove is to be milled into a metal block that's 8 inches long. So in other words, it's an 8-inch long groove going across the block. Allowable cutting speed is 80 feet per minute between the tool and the metal. And the feed rate is 6/1000ths of an inch per revolution. That is assuming that's adjusted for the number of teeth on the mill. So it's got everything in consideration. So a 3/8 inch groove, of course, assumes a 3/8 inch diameter mill. So go ahead and figure out the time required for that. What's the first thing we have to do here? RPMs. How do you find RPMs? Okay. By 3/8. Okay, so 3.82, which is just the 12 divided by pi, times 80, which is our surface cutting speed, divided by 3/8, which is our diameter. So let's do that. Gives us 815 RPMs. Sound right? Now what? Okay. Take the length of the cut, 8 inches, times our velocity, our movement, which is the number of RPMs times the inches per RPM. So 815 times 0.006. So to punch this one in, it's 8 divided by, we have to use our parentheses now, 815 times 0.006. So 1.636 basically. What unit of time goes on there? Is that seconds? What is it? Minutes. And if I wanted to convert that into minutes and seconds, of course that is 1 minute. And on the calculator, what I'd do is I'd subtract the whole number. I'd subtract the 1, and then times 60 to make it seconds. So 38 seconds about. So a minute and 38 or 39 seconds is what it's going to take. What do you think? Not horrible? Okay then. Well, back to dealing with our angles and geometry and stuff. We've already talked a lot about different types of angles, right angles, acute angles, obtuse angles. Today we're going to start talking about triangles and how they're classified. And one of the ways we classify triangles is by their angles. We can classify a triangle, and we'll start out with the simplest one, at least what I think is the simplest one. If I can get this to erase, I don't know what's going on here. There we go. The right triangle. A right triangle, of course, is any triangle that has a right angle in it. So, since there's that right angle in it, that's a right triangle. All triangles are classified by their largest angle. If you notice, in a right triangle, the largest angle has to be that right angle, because we talked about it before. What do all three of the angles of a triangle have to add up to? 180. Very good. And if this is 90 degrees, that means there's only 90 degrees left between the other two angles. So neither one of them can be bigger than 90. So that right angle has to be the largest angle in the triangle. So then we can have a triangle that's like this. We can have an angle bigger than 90 degrees in a triangle. We just can't have two angles that are 90 degrees or bigger. This is what we would call an obtuse triangle because it has an obtuse angle. And of course, again, because it adds up to 180, we can only have one obtuse angle in the triangle. The other two angles must be acute, must be pretty small. And then the third possibility with our angles is to have a triangle where all the angles are smaller than 90 degrees, or acute angles. So in this triangle, the largest angle is still smaller than 90 degrees. It's still an acute angle. Well, we could also classify triangles by their sides. We'll start out with the simplest and most common, where all sides are different lengths. So this mark, the different marks means that each side's a different length. If two sides had the same number of little hash marks on them, that means they're the same. This is what we would call scalene, meaning none of the sides are the same. What do we call it if we have two sides that are the same, like this? Isosceles. And then, of course, we're going to have a triangle where all three sides are the same, like this one, which is equilateral. Very good. And again, you're going to have to learn to use those marks. You see those marks to identify whether the sides are equal or not. When we go to identify a triangle, we actually, in many cases, use both. For example, we might have something like this. If I was identifying that with the angles, what would it be? Right. If I was identifying it with the sides, what would it be? Not equilateral, isosceles. So that is called an isosceles right triangle. Or we might have, what do I put in there? Something like this. It's an obtuse, there you go. So it's an isosceles obtuse triangle. Or we could have, this one would be called isosceles acute. Very good. Is it possible to have an equilateral right triangle? No, it is not. Equilateral triangle is an equilateral triangle, period. There is no other classification of angles because an equilateral triangle must be acute. There's no such thing as a right equilateral or an obtuse equilateral. In fact, one of the rules in triangles is, let's label some sides here. Let's call that 8 inches, 13 inches, and 15 inches. One of the rules in a triangle is the smallest angle must be opposite the smallest side. So if I call these angles A, B, and C, which angle here must be the smallest? A must be the smallest because it is opposite the 8-inch side, the smallest side. Which angle must be the largest? C, because it is opposite the 15-inch or the largest side. So now in an isosceles, or an equilateral triangle, I should say, if all the sides are the same, which angle is the biggest? None of them. They're all the same. How big do those angles have to be? Well, the whole triangle has to add up to 180, and they're each the same, so divided by 3 would be 60 degrees each. So in an equilateral triangle, we always have 60-degree angles. Let's say we have an isosceles triangle here, and this is 40 degrees. What do we know about these two angles? Not necessarily 60. But we know those two angles have to be the same. Why? Because they're opposite sides that are the same. If they're opposite equal sides, the angles must be equal. So this is 180 degrees minus the 40 leaves us with 140. We divide that by 2, gives us 70 degrees each. So, in your notes, find angle A and angle B for me here. Okay, so looking at this, it's an isosceles triangle, so it has to be at least 2 angles that are equal. Which 2 angles are equal? A and 31. Yes, so this is 31 degrees. How do we find B?
62 from 180.
Perfect. We have the 31 and 31 make 62. Subtract that from 180. It's 118 degrees. Perfect. Well, let's try something just a touch more complex. Oh, complex is always good. Actually, that's not what I want. I want to find that angle right there, angle A. I'll give you some time to find it. So, talk me through it. So 57 and 61 is 118. So 180 minus 118 is 62. Good. What's that one give you? Okay, so then what? Which is 134. Subtract that from 180 is 46. What's that give us? Okay. Okay, so you divide that by 2. 67 degrees. Okay. That'd be 67 up there as well. If you don't get the picture yet, you can see that 180 degrees is a very important benchmark for a lot of things. Angles adding up to a straight line, total angle sum in a triangle. It comes up a lot. Okay, well, let's take on the next step then. Let's look at what happens when we get into figures that have more than 3 sides. We're going to start looking at polygons. You quit? Well, a triangle is a type of polygon. I mean, you can have, a polygon can have 3 sides. That's a triangle. As we keep going, of course, if you have 4 sides, that's called what?
A rectangle. Or a rectangular polygon.
Rectangle is a special type of this. Square is even more special. Quadrilateral. Quadra meaning 4, lateral meaning side. I put an extra T in there, I guess, didn't I? No extra charge for the extra T. So, quadrilateral, there are special types. There's rectangles. There are squares, which are actually a special type of rectangle. There are parallelograms. Including trapezoid. There's a rhombus, which is a special type of a parallelogram. Anybody know what all those terms mean? Mm-hmm. What's a parallelogram?
Parallelogram is when top of the shape and bottom of the shape parallel.
Okay. Parallelogram is when opposite sides are parallel. So, yeah, top and bottom are parallel, left and right are parallel. But the angles themselves don't necessarily have to be right angles. Now, you look at this in light of what we learned yesterday. You can think of this as being parallel lines cut by transversals. What's the relationship between this angle and this angle have to be? They have to add up to 180. And the same with this angle here and this one. They have to add up to 180. And these opposite corners, these two have to be equal, and these two have to be equal. So in a parallelogram, once we know one angle, we know all of them. If I tell you that this angle up here, let's say that they tell you that this is 59 degrees. What's this angle have to be? 180 minus 59, or 121. What's this one have to be? 59. And this one? 121. Not so bad. A rhombus is nothing more than a parallelogram where not only the opposite sides are parallel, pretend those are parallel, but all sides are equal. Rectangle, we know that one. Like a rhombus, a rectangle is a special kind of parallelogram. It's a parallelogram, except, and obviously in a parallelogram, these two sides are equal and these two sides are equal, right? Same in a rectangle. These two sides and these two sides are equal. But what's special about a rectangle from a parallelogram? You said 90-degree angles. If one corner is a right angle, they all have to be right angles. So all you need to know for a rectangle is it has one right angle and the rest all have to be. A square is a special type of rectangle where all four sides are equal and it has a right angle. So a square is actually a rectangle. It's also a rhombus, and it's a parallelogram. It fits into several different categories. A rectangle is also a parallelogram. A rhombus is a parallelogram. Trapezoid, of course, is where you have one pair of opposite sides that are parallel and the other pair is not. And then, of course, you just have generic quadrilaterals that they have four sides and they don't follow any rules. Like that. There you go. They do what they want, right? What do we call it if they have five sides? Pentagon, yes. Six sides? Hexagon. Seven sides we usually skip over. 8 sides? Octagon. Oops, got it. Now, if you're really curious, 7 sides is a septagon. 9 sides is nonagon. 10 sides is a decagon. But 5, 6, and 8 are usually the more popular ones. When we get above a quadrilateral have all the special names, the parallelograms, rectangles, squares, rhombus, trapezoids, whatever. We get beyond that, we don't have all the special qualities anymore. What we have is we have regular and irregular. Regular means, no, not that easy. Regular means all sides equal and all angles equal. So what you would normally think of as a hexagon is a regular hexagon, where you have, well, we'll pretend this is regular, it's close enough. All the sides are equal, and all the angles are equal. Like that. What's that? Kind of, yeah. Irregular, of course, can be anything. There's also convex and concave. If you're looking at them, concave means from the inside all the angles face in. Convex would mean one of the angles faces out, like this. There is a convex polygon because one of the interior angles is bigger than 180 degrees. or the inside of the angle is on the outside of the figure, if you want to look at it like that. So we talked about angle sum a little bit yesterday, how the triangle has to add up to 180 degrees. I want to look at how other figures, how we find that for other figures. Let's look at how we came up with that for a triangle. What we're going to do is we're just going to assume we're walking around our triangle. We're going to start right here walking in this direction. Of course, we get to this corner of the triangle and we turn. We start walking in this direction. When we get to this corner, we turn again. Walk down here, and we get here, we turn again. How far have we turned here? A complete circle, 360 degrees. So if I label these angles here, D, E, and F, those angles have to add up to 360 degrees, correct? If I label the angles of my triangle, A, B, and C, well, these two angles have to add up to how much? 180. These two add up to 180, and these two add up to 180. So A plus B plus C plus D plus E plus F has to add up to 180 three different times, or 540 degrees, correct? If I subtract out D, E, and F, which is 360, I'm left with 180 degrees. So A plus B plus C equals 180 degrees. This can apply, though, for any polygon. Each corner is going to have how many degrees in it? Well, we had 180 here for these two, right? So it's the number of angles, or the number of sides, we're just going to call it N, can represent either one, number of angles, number of sides, times 180, minus these exterior angles. No matter how many of them there are, you're still going to make one complete turn, which will be 360 degrees, correct? Subtracting 360 degrees. So if we have a figure, and that's actually the angle right there, the formula. The book simplifies this formula. What it does is it factors out 180 degrees, and it does this. It's 180 times n minus 2. If you look at it, it comes out to be the same, because 180 times 2 is 360. It's the same thing. So anyway, let's look at a four-sided or a four-angular figure, a quadrilateral. What's 4 times 180 would be 720, minus 360 is 360 degrees. We talked about that yesterday. A four-sided figure has 360 degrees. What would be the angle sum of a five-sided figure? Well, 5 times 180 is 900, minus 360 would be 540 degrees. Or I could have used this formula here. 5 minus 2 would be 3. 180 times 3 is also 540. So for a six-sided figure, how many degrees? What would be the angle sum? Go ahead and figure that out quick. $720. Very good. I usually do use this one because it's a little bit easier to use. 6 minus 2 is 4. 180 times 4 is 720. Eight-sided figure. What'd you come up with? 1080. Very good. 8 minus 2 is 6. 6 times 180 is going to be 1080. Not so bad? Okay. So now that we're dealing with these polygons and everything, let's take a look at some special rules for some special polygons. If we're looking at regular polygons, I'm going to attempt to draw a regular hexagon again. You might have to use your imagination a bit. So that's a regular hexagon. If I draw a diagonal from one angle to its opposite angle, what does it do to this angle here? What's that? Well, symmetrical, it bisects it. It cuts it in half. These two angles are the same, if that's what you meant by symmetrical in Bisector. Yeah, it cuts each of those angles into two equal angles. Cuts them in half. And that happens a lot with any regular polygon. If you draw a diagonal from one angle to the opposite angle, the opposite vertex, it'll cut the angle in half. Now in triangles, we don't even have to have a regular triangle. Of course, a regular triangle would be equilateral. You can't draw a diagonal in a triangle because there's no opposite vertex, is there? That only works if you have an even number of vertices or even number of sides. But in a triangle, what we can do, we're assuming this is equilateral, is we can do something called an well, there's several different names. We're going to talk about an angle bisector. We're going to talk about a median. And we're going to talk about an altitude. We've already talked about finding the area of a triangle. That when you find the area of a triangle, you have to have the base. And you have to have a height that's perpendicular to the base that goes out to that opposite vertex. That is called an altitude. But when I'm dealing with a special triangle, like an equilateral triangle, if I draw in that altitude, so it's at a right angle to the base, I'm going to consider this to be my base, goes up to that opposite vertex. Well, that altitude, because this is equilateral, this is a right angle as well, it's going to cut this angle into two equal angles. So it is also an angle bisector. An angle bisector is a line through an angle that cuts the angle in half. Well, it also takes this side here and it cuts it in half. This piece is going to be equal to this piece, which makes it also a median. Why is that? How can we prove it? Well, we use congruent triangles. I'm going to draw a little bit bigger version of it here. So these sides are all three equal, which means this angle is 60 degrees, this angle is 60 degrees, and this angle is 60 degrees. By definition, an altitude forms a 90-degree angle here. Well, because that's a straight line, if that's 90 degrees, this better be 90 degrees as well, adding up to 180. So now if I just look at this triangle on the right side, I have 90 degrees, 60 degrees adds up to 150, which means this angle here has to be 30 degrees, which is half of the 60. The exact same math will exist over here. So that proves right there that it's an angle bisector. It cuts that angle in half. Now, since we found that all of these angles are the same between the two triangles, we know that at the very least the two triangles are similar. But we also know that this side and this side would both be the hypotenuse of each triangle, and they're the exact same length. So if you have two similar triangles, if corresponding sides are equal, like this side and this side are corresponding sides, those would be the sides that would be, the before and after of the enlargement. If they're equal, that means the two triangles are equal. So if these two triangles are equal, then this piece and this piece have to be the same, which proves it's a median. It divides the opposite side in half. Well, not only does that work with equilateral triangles, more often than not, you guys run into isosceles triangles like this. And in an isosceles triangle, as long as we use the angle that is between the two equal sides, we get the same effect. If we draw an altitude from there, like that, it cuts this angle in half, and it cuts this side in half. And I bet you're wondering, how is that helpful to us? Well, we end up with a lot of isosceles triangles. Start dealing with things like V-blocks. one of the rules we're going to find out is the distance when you have a round piece in a V block. The distance from the vertex of the V to this point of tangency and this point of tangency are the same. So that is an isosceles triangle. If we cut it like this, that means we cut this angle in half. Which means when we go to do our trig, we now have a right angle, and we know this angle to be half of the V.
That looks like if you solve that problem, it'd be much easier that way.
You can.
Yeah.
That's why I did it before using just the aspect ratios, you know, the rise and the run and doing that. Once we bring in trig, it's going to make this a lot easier. That's why we went over all that. Little bit of a review problem for you. I know we did this last semester. Find x. How do we find it?
A squared, 5 squared, plus 12 squared,
Yeah. So you see either 5 squared plus 12 squared equals x squared, or we can just do that, square root it. So 5 squared is 25. 12 squared is 144. That adds up to 169. And the square root of 169 is 13. So x is 13. So 13 inches. Slightly different note. Find x. Different on this one. Got to work backwards. So either do x squared plus 15 squared equals 17 squared, or you can just say x is equal to 17 squared minus 15 squared square root. Either way is fine. What do you come up with? X is 8 millimeters. Perfect. We're 6 minutes early, but that's okay. I am going to give you in the packet I just handed out, page 286, 1 through 24, and on page 295, 1 through 24. These should go really quickly. They're just knowing what the rules are, figuring out what they are. I would recommend you go through all of these because there's a lot of rules, and the only way to get good at them, bless you, the only way to get good at them is just to practice them and make sure you recognize them. Because these are things that are going to come up in our trig problems. If you don't recognize them, you're not going to know where to go with it.